all about gases. And you already have some familiarity with this. We've been looking at models of different states of matter, and we did the lab at the beginning where we actually determined the relationships between temperature and pressure, or volume and pressure. So, to start with the basics, you want to have a picture in your mind of what a gas is. And that picture in your mind should mean atoms and molecules far apart, moving quickly and randomly. All right. So to reinforce that picture, here is a sample of air. I'll zoom in a little bit. Oh. So there's a sample of air. You can see mostly these blue diatomic molecules. What do you think those blue diatomic molecules are? Not oxygen, because oxygen is not the main component. Nitrogen. The red diatomic ones, you may not be able to see in the room that they're diatomic, but those red diatomic ones are oxygen. If you look really closely, you will find in this given chamber maybe one or two monatomic atoms, which represent argon, which is a minor component of air. And then everything else in air, at least in dry air, everything else would be in such small quantities that in a box this size or in a sample this size, you wouldn't actually have any molecules of anything else. Depending on the humidity, you might have some water in the box. So at 30% humidity, a box this size has one water molecule. At 60%, it would have two water molecules. Maybe. Oh, yep, I see two of them. At 90% humidity, 3 molecules. So air is mostly nitrogen and oxygen, traces a little tiny bit of argon, and then some water vapor, traces of other gases. What does the percent humidity mean? It's complicated. So relative humidity is like compared to what the air would be if it were saturated with water vapor. And I don't want to go into the definition of it. Yeah, but it's more of a meteorological term. So this is 90% as much water vapor as air can possibly hold at this temperature, which I think is probably room temperature. So that's the picture you want to have in your head. Remember that we have some molecules that'll be faster, some that'll slower. So I changed it so that now they are colored based on their kinetic energy. The red ones now are the ones that are moving quickly. The blue ones are moving more slowly. Oops. And I don't know what just happened. But I didn't actually pause it. It just got upset. Oh well. So whenever we talk about gases, keep that picture in your head. Particles far apart, moving quickly. And then we'll talk about 4 different variables with a gas. It's pressure, temperature, volume, and number of moles. 3 of those are really straightforward, or we've talked about before. Temperature. What exactly is temperature? All right, measure of the average translational kinetic energy of the particles in a sample. And you want to remember the Boltzmann distribution. We've seen a bunch of times now. That's by design, by the way, because it's sort of an abstract thing, and we introduced it at the very beginning of the year, and we keep showing it to you because it'll show up on the AP test at some point, and you want to just be familiar with it. But remember, it's that graph that has this tail at the end, and it's kinetic energy and number of particles with that kinetic energy. And so there are some particles with low kinetic energy, a small amount of particles with very high kinetic energy, and then the average somewhere in the middle. All right, so that's temperature. How about volume? All right, measure the amount of space taken up by the sample. For a gas, essentially that just means the size of its container, because a gas will fill its entire container. So really this is the size of the container. Gas particles just keep moving in straight lines until they bump into something. So they'll keep going until they hit the wall of the container. And then number of moles. Yeah, it's really measuring the number of particles. So really number of particles divided by Avogadro's number. Because in any like measurable sample of air, not like the simulation where we could actually count the molecules, that simulation had a box that was probably like a couple of nanometers on each side. In any measurable sample, you're going to have way too many atoms to count individually, or way too many particles to count individually. All right. So those three are pretty straightforward. The fourth one, pressure, a lot of times we have an intuitive sense of it. But what does pressure actually mean, and where does it come from? All right, it has to do with force. Let me just get my... All right. Has to do with force. Now, what are those particles exerting force on? Danny? The walls of the container. Why are they exerting force on the walls of the container? Or how are they exerting force on the walls of the container? By hitting it. Yeah. So pressure is caused by gas particles bumping into stuff. All right. So pressure is the force exerted on the walls of the container except it's a little more complicated than that. Now, if I don't have a textbook up here. Is there a heavy object nearby? All right. Now, I really should use a textbook. All right. I can drop this textbook, and if I drop it from the same height, no matter what, when it hits the ground, it's going to exert the same amount of force. Okay? But now, Sam, if I'm going to drop the textbook on your foot, I'm going to give you three options. I can drop it flat, like this. I could drop it on the edge like this, or I could drop it on the corner like that. Which one would you prefer? That's not an option. All right. Well, who would like to make the who would like to make the choice? Cat. All right. You'd rather I drop the textbook flat. Why? All right. If it hits on the edge or the corner, it'll hurt more because it's pointed. And why does the fact that it's pointed matter? All right. It's about concentrating force over a certain surface area. If the book drops flat, that force is all spread out over a wide area. Lower pressure. If you drop it on the corner, now all that force is concentrated in a small area. That's a large amount of pressure. So pressure has these two components. It's force divided by surface area. So, for example, if you fill your car tires, what are the units of pressure that are given? Yeah, pounds per square inch. Of course, in science, we generally don't use pounds per square inch, but that for scuba diving or filling your tires, it's always going to be given in PSI. Yeah, so one thing that this points out is it's impossible to have negative pressure. You can hear the term negative pressure, and the term negative pressure is usually used to describe a pressure differential between two things. So, for instance, science rooms like this are supposed to be kept at, quote, negative pressure, which means we have that fume hood back there that's constantly pulling air out of the room and keeping the pressure in the room lower than the pressure, say, outside of the room. So that's essentially pulling stuff out. But that doesn't mean the pressure is actually negative. You can have negative differences in pressure, but not negative pressure. So the question is, does that mean pressure is not a vector? I would say pressure is not a vector. But the force is a vector. Yeah. All right. We have a student offering a joke about Einstein and Pascal playing hide and seek. And Newton. Okay. I do not know it. Pascal, Einstein, and Newton are playing hide and seek. Einstein closes his eyes. Pascal runs through the forest. And Newton just draws a square on the ground and stands in it. When Einstein opens his eyes, he sees Newton and says, "Woohoo! I found Newton." So Newton says, "No, no, you didn't find Newton. What you found is 1 Newton over a square meter, which is Pascal." So to get the joke, you have to know that newtons per meter squared, the unit newtons per meter squared, these are called pascals. So I like the joke. That's nice. I'm pretty sure Newton would not have known that newtons per meter squared were called pascals because that would have come later. But that's all right. All right, so what causes it? We said It's gas particles bumping into stuff. So whenever you think about pressure, think about, oh, there's gas particles bumping into that thing. You experience pressure differentials usually when you ride an elevator up a tall building, climb a mountain, do anything where you're changing altitude because the external pressure is changing. Any idea why you actually feel that in your ears? All right. All right. So you have an eardrum, and on the inside of your eardrum there's some enclosed gas. And generally that enclosed gas is going to have the same pressure as the air outside. So you have the same number of particles or same force pushing on the inside and the outside. And so you don't feel anything. Now, when you go somewhere where there's a lower pressure, the pressure inside is still what it was, let's say at sea level, and now the pressure outside is lower. So what you're feeling there is more particles hitting the inside of your drum than particles hitting the outside of your drum. And the biology part, the anatomy part is that you have these things called eustachian tubes in the back there that those can get open so that air can get exchanged between the outside and the inside of your ear. And when that happens, pressure equilibrates, and now you don't feel it anymore. Equilibrates. I believe that is the correct pronunciation of equilibrate. Would you say equilibrate? So the question is, will your ears pop if you're hiking a mountain? And the answer is, yeah. I mean, if you go really slowly, and particularly if you're swallowing a lot, because swallowing tends to open up that tube and allow exchange of air in the back, with the back of your eardrum. So if you're going really slowly and you swallow a lot, you probably would not notice it because it'll constantly be equalizing. But, you know, it's when you have a change in pressure and you don't allow that to equilibrate, that's when you feel it. You know, a lot of times people suggest chewing gum while, you know, when an airplane takes off, or when you take a baby on a plane, feeding them a bottle, because when they're swallowing a lot, that helps equalize the pressure. So the question is, would this have been a well-known phenomenon before elevators and airplanes, and you know, when people changed altitude more slowly? And I would say it might have been well known to scientists. Um, okay, good point. Good point. I'll come back to that. It might have been well known to scientists, but probably the everyday person, you know, if you were like, oh yeah, my ears just popped from, they would have been like, what? I've never experienced that. Because if you lived at the same altitude your whole life, you probably wouldn't have experienced it. It's a good point. But but Sam pointed out that anyone who swims and swims, you know, any distance underwater, there's a rapid change in pressure there. And so people who swim would have recognized that phenomenon. All right. So pressure is gas particles bumping into stuff. That's the main concept that you need to keep in mind. So when you change volume or temperature, we've already looked at this. We did this in the lab. If you change the volume, what's going to happen to the number of collisions? So if I increase the volume of my container, what will happen to the number of collisions? All right. So collisions are less frequent. And if collisions are less frequent, what will happen to the pressure? Pressure will drop. If you increase the temperature, collisions will be more frequent. Because the particles are moving faster. And so more frequent collisions means more pressure. And if you increase the number of moles of gas particles, or like we said, if you were hiking up a mountain, what happens is the air gets thinner. So in a certain volume of air, there are fewer gas particles. So that's like decreasing the number of gas particles. When you change the number of gas particles, if you increase it, what does that mean in frequency of collisions? More frequent collisions. So pressure increases. So conceptually, I think this is probably the simplest concept we've dealt with to this point in the year. As long as you keep the picture in your head, those relationships are pretty simple to derive. Now, it turns out that mathematically these relationships are really simple too. You can imagine lots of mathematical relationships where when volume increases, pressure goes down. Or lots of mathematical relationships where when temperature increases, the pressure increases as well. But it turns out we get pretty much the simplest mathematical relationship we can get. And it's called the ideal gas law. And the idea is this. If you take the pressure times the volume and you divide it by the number of moles times the temperature, you get a constant value. This is known as the ideal gas constant. We'll see, actually, the ideal gas constant is more universal. It applies to things beyond just gases. So R is going to come up later in the year, and you're going to be like, wait, is that the ideal gas constant? And I'll say yes. So when we're dealing with thermodynamics and things like that, R rears its head again. So R originally got named the ideal gas constant because this is the first place it was used, and then people studying thermodynamics and reaction kinetics found, oh wait, the same constant applies here. So that is a number. It is on your formula sheet. The one thing you need to be careful of when you're using this equation is that R can have different units. So when using this equation, make sure that the units of R match the units of pressure that you're using. So this can be 62.4 liter torr per mole Kelvin, or it can be 0.0821 liter atmospheres per mole Kelvin. Well, it's on your formula sheet, so you don't necessarily need to. But what I would write down is make sure the units of P and R match. Nick? The question is, why couldn't they come up with one unit? Like, well, if you think about it, units are really, units on a constant like that are really the translation between nature's units and like our units, because we use different units to measure stuff. So that universal, that constant, can be measured in different units as well. Just like my height, you could say, oh, your height should have a single number, but if I go to Europe, my height's going to have a different number than it has here because it'll be measured in different units. All right, the question is, does that ideal gas equation always apply? And we'll talk in a little bit about situations when the ideal gas law doesn't apply. So we usually assume this to be true. But recognize that it's not always, it doesn't always work. And there'll be more to come on that. The question is, are we going to use real gas law? We'll bring up a much uglier equation that attempts to deal with the fact that this ideal gas law doesn't always hold true. But we're not going to do any calculations with said ugly equation. So unless you are told otherwise, you can assume gases are behaving ideally. Okay? When you're solving problems, when you're doing calculations. You would use this anytime you know 3 of the variables and you want to know the 4th. Okay? Then we have what we call the combined gas law. The combined gas law is just recognizing that, all right, if PV divided by NT is a constant number, then if I have 2 different moments in time, if I measure pressure 1 times volume 1 divided by number of moles 1 times temperature 1, that'll equal P2 times V2 over N2 times T2. So we use this when conditions are changing. And the thing is, if something is remaining constant, you drop it out of the equation. So this combined gas law you can use in a variety of situations. Let's say number of moles and the volume are constant, then it becomes a simpler equation. So if n and I said n and v, and then I wrote n and t. Yeah. If n and v are constant, then we get just P1 over T1 equals P2 over V over T2. Each of these individual, quote, laws was discovered by someone else, so they all have names, and I don't care if you know their names or not. There's Charles' law and Boyle's law and Gay-Lussac's law and Avogadro's law, and why bother? So we have those 2 gas laws. Take a moment and answer this question. All right. The key here is units matter. We haven't done a lot of calculations in the class to this point, and guess what? That all changes very soon. Math is making a big comeback. So this unit is really our first introduction to starting to use a lot more math. Chapter 10, not so much math. Chapter 11, math. 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, all math. Lots of math. So if you've appreciated not having to do a lot of calculations to this point, well, hope you enjoyed it. It was a good time. There will still be concepts. There'll still be lots of concepts for the rest of the year, but we're going to be looking at a lot of things mathematically. This is really the very simple end of the calculations we'll be doing, just solving a simple equation. So my pressure is 1.23 atmospheres. My temperature is 15 degrees Celsius. Am I going to plug that into the equation? No. So one thing I forgot to point out on the previous slide, we always need to use temperature in Kelvin. So this is 273 plus 15, 288 Kelvin. So always use Kelvin. All right. Volume we're given is 3.7 liters. Number of moles is what we want to know. R, which R value should I use? 0.0821. So I personally, when I solve equations, like to solve with the letters and then plug in. Some people like to plug in and then solve. But I would take my equation and solve it. I'll move this n. I would solve it for n and say n equals PV over RT. So that's going to be 1.23 atmospheres times 3.7 liters over 0.0821 liter atmospheres per mole Kelvin times 288 Kelvin. Let's see if my units work out. I have atmospheres on top and atmospheres on bottom, so those go away. Liters on top, liters on bottom, those go away. Kelvin on the bottom, and then Kelvin on the bottom of the bottom, so those go away. And I have 1 over moles on the bottom, so now when I solve, that's going to become moles on the top. So N is going to be, I don't know, some fraction of a mole, maybe about a, sorry? 0.193. I was going to say about a fifth of a mole, so I was close. So the question is, will different elements have different relationship between number of moles and the pressure involved? And the answer is no. The answer is any ideal gas, no matter what the particles are, has the same relationship. So different elements do not have anything different for this formula. So if this question had said how many moles of nitrogen gas, the answer would be the same. If it said how many moles of argon gas, the answer would be the same. Same number of moles. If it's so if it's the same number of moles at the same temperature and volume, it'll always have the same pressure. Doesn't matter the identity of the gas. Okay? The only time you care about the identity of the gas is if you're asked about mass. Because with mass, now they have different molar masses. But this equation applies equally to any gas, and none of those parameters is different based on the identity of the gas. So the question is, wouldn't the mass of the gas particles affect how much force they're exerting? The answer is, well, mass is an important factor there, but temperature, remember, measures kinetic energy, which already factors in the difference in masses. So, you know, so it doesn't matter what their mass is, they'll still have the same amount of average kinetic energy, which means they'll still follow the same rules. We will see some phenomena where we have to consider the different masses, and they behave differently because of that. All right. We'll pick that up again next week.